So you want to get an effect like this one in Blender using an array of objects. Let's see how to do it. We start creating a cube and applying an array modifier, let's say with 10 elements, and let's increase a bit the spacing between them. Here it is. So the problem of an array is that all the objects inside the array are all alike. They all look the same. For example, if I add a material to this cube and we add a texture, an image texture connected to the base color, we create a new image of type color grid. The result is something like this, which is not what we want. Well, the trick here is to use a property which is not well known of the array modifier, and this one, UVs offset U and offset V. Let's work with the U offset, and let's set this value to 1 divided by the number of elements in the array. So in this case 1 divided by 10, or 0.1. Now we have to go to the UV editing workspace, and we have to perform an UV mapping for this cube. In this case I will just use a cube projection mapping, which is a very easy mapping where all the faces are projected over the entire UV space. What I need to do now is to shrink this mapping by a value which is a bit less than the U offset we just selected in the array modifier. So in this case I will scale by a factor of less than 0.1. For example, I press S, 0.1, this is my mapping scaled by 0.1, and I will make it a bit smaller. Okay. Now let's move it here in the top left corner. And what's the effect of this parameter in the array modifier? Well, the idea is that the entire UV space has a U coordinate that goes from 0 to 1. This is 0 and this is 1. And our cube is currently mapped here in an area going from 0 to at maximum 0.1, because we scaled it this way. What this parameter does is to shift the offset in the UV space for each element of the array. This means that the first cube will be mapped in this area of the UV space, but the second cube will be mapped in this other area between 0.1 and 0.2. The third cube will be mapped in this area between 0.2 and 0.3, and so on, with increments of 0.1. This is the offset U parameter we have just chosen. And in fact, if we visualize the effect, here it is. As you can see, the cubes are not all equal, but they change color. Now, how can we exploit this feature to get our effect? Well, it's not difficult. We go to the shading mode. Let's delete the image texture. I will change the base color to black, and I will set an emission color to red. And what I want to do is to modify this strength attribute in order to change the emission color for each cube separately. In order to get this result, we can start with a UV map node. This is just a node containing the UV coordinates of our object. We are interested in, for now only in the U component. This is the horizontal coordinate in the UV space. So we can connect this output to a separate XYZ node. And so I will work only with the X parameter. This is the same as the U parameter in the UV space. So this X will range from 0 to 1, and I will change it by passing it through a math node, and in this case I change the type of math operation to multiply, and I multiply this value by the number of elements in the array, in this case 10. So the output of this node is now a number, a real number, continuously going from 0 to 10. Finally, we connect it to another math node, in this case of type floor. This node takes a real number in input and returns an integer number. It rounds the real number down to the closest integer. So what will be the output of this node? Well, the UV coordinates for those cubes are a number going from 0 to 1. This is just the U coordinate, of course, but we have multiplied it by 10, so it's a number going from 0 to 10, and then we are computing the floor of this value. So from here to here we have a number, a real number going from 0 up to 1, and by the effect of this floor node, all the points of this cube will have a value of 0, sorry, not 1. Then the same for the second cube. The output of the multiplied node will be a number, a real number between 1 and 2, and the effect of the floor will give always the number 1 when working on the UV space of this second cube. And so on, we can assign to each one of those cubes an integer number. 0, 1, 2, 3, 4, up to 9. So those nodes work as an object index inside of the array. Let's put them in a frame, and I will call this one object index. Now, in order to work with those values and have an animation, we need the frame number, and this is easy to do if we use a value node. This is just a single number, and here in the field of the value we can type hash frame. This way, here the value node will always contain the current frame number. As you can see, if we move along the timeline, the value here is changing. How can we use it? Well, we can feed this value to another math node of type rounding ping pong, and the scale factor here will be set to the number of elements in the array minus 1, so in this case 9. What's the effect of this ping pong node? Well, as the frame increase from 1 to 9, the ping pong node will output the same value. But once you reach frame 10, something changes. In this case, the output of the ping pong node will start going backward, so it will not be 10, but it will be 8. then the next frame will be 7, and so on. So as you move in the timeline, the output of this node will be a number going from 0 to 9 and back. And it will continue like this forever, back and forth between those two values, 0 and 9. So we can use this value as an object selector. Let's create a frame for this. Here it is. This is the object selector. How can we use those two values? Well, for example, we can simply compare them. What happens if we use a math node of type compare and we compare those two values? Well, this will output 1 only if the frame number, the object selector, is equal to the object index of a specific cube inside this array. So if I connect this output value to the strength of the mission, here it is the result. As we move in the timeline, the frame number will select each time a different cube, so it will go back and forth like this. Of course, if you don't like the speed of this effect, which is now very fast, you can simply scale the frame number with another math node. For example, we can divide the frame number by, let's say, 3, and as you can see now it's much slower. But we can improve this result by creating a color gradient, so also the cubes near the selected one have an emission strength different than 0. In order to get this effect, we don't use anymore a compare node here, but we will change it to a subtract. So what's the effect of this subtract? Well, let's see it here. Basically, if the selected node is, let's say, this one, the difference here will be 0. It's the frame selector minus the object index. They are equal, so the difference is 0. And then the cube next to the selected one will have an output of 1, this one will have an output of 2, and so on. And on the other side we have the same, but with negative values, so -1, -2, -3. I want to use this value as a distance from the selected cube. So in order to be a distance, we need another math node, because we have to take the absolute value, of course, because distances must always be positive. And the problem here that this node now outputs a value between 0 and 9, because this is the maximum distance we can have between two cubes. The one with a value of 0 and the other one with value of 9. And I want to scale this output in the range from 0 to 1. In this case, we can get this effect by another math node, and we can divide everything. Since we are going from 0 to 1, we can divide by from 0 to 9, sorry, we can divide by 9, and here it is the result. But this is not exactly what we wanted, because I want the selected cube to be bright and the other one darker and darker, and now we are getting the opposite effect. But we can solve this issue by another math node, and in this case it will be a subtract node. we subtract 1 minus the value we just computed. So this is just the inverse of what we computed before. And now, yes, the selected cube is has the brightest emission, and the other ones close to him have an emission which is getting lower and lower. But the problem is here is that the gradient is very large. We can solve this problem by using a float curve node. Here it is. This is basically a function that will apply a nonlinear map to the input value. For example, I can build a function like this, which makes the color gradient more evident. If I use a curve like this, as you can see, the gradient is narrower. If I use a function like this, it's much wider. This is too much. So let's create a curve like this one, and here it is. This is the gradient I like. And basically, we are done. I hope you liked it, and see you next time.